somewhere around 21.9.
I think it is 20. Oh wait, no, never mind, I put it in wrong.
21.9, yeah.
It is 21.9?
How y'all got that?
15 squared plus 16 squared, square root.
So if I add those together and then get the square root of that?
Yep. So 15 squared, so that's 225
25,
plus
256.
281.
and the square root of 481 apparently is 21.9. So the magnitude of the final momentum, or sorry, magnitude of the initial momentum is 21.9 Descartes. I'm gonna write this in abbreviated form just so you sort of get used to it. Magnitude, use absolute value signs. So that long sentence I just said, this is the shorthand. If the objects stick together, what is its final? We'll do final velocity and then final speed. So if they stick together, V final and V final. Velocity with the vector symbol, speed without the vector symbol. Well, I know what the initial momentum is. What's my final momentum going to be?
I got lost trying to pay attention to the math.
All right.
I mean, to the math. What you said again?
All right, so what is my total final momentum going to be?
Is it 21.9?
That's the magnitude of it. I'm looking for the vector.
Oh, it's the 15D I hat plus 16D J hat.
Yeah, it's the same thing as it was before,
Okay.
which is what you were going towards also, but I wasn't looking for magnitude, just looking for the actual value here. So I have so P final, gotta be P initial, which is 15D I hat plus 16D J hat. That's gotta be equal to my mass times my velocity final. What's my final mass?
13.
And then V final.
Where did I get 13 from?
You told me.
Your question.
They stick together.
Oh, I didn't hear that part.
Yeah, if they stick together.
Okay.
And so my math problem is 15 I hat plus 16 J hat. Yeah, the math problem still has those in there. Is equal to 13 V. That's the math problem. How do we solve for V?
Division.
Divide by,
13.
all right. So we divide this side by 13. We divide the other side by 13. We're gonna divide both of them by 13, not just one of them, as I've seen way too many times. We'll divide the 15 by 13 and the 16 by 13. So that's V is equal to V final, putting the proper notation back in. Let me just go the shorthand route, just write the fraction, 15/13
I hat.
plus 16/13 J hat. And we gotta throw units in there somewhere. Yep. Question is, where do I write it? So here? You feel like I'm setting you up for something?
I was gonna say, I think you is.
I would take off probably a point for that. The
So-
way it's written, and this is, and not every instructor is picky about this one. There's some things I'm just hyper picky about and some things I'm not. Units apparently is one of those things. Again, childhood scars, it's hard to escape them. The way you've written it right here, that meters per second goes for the second term, and we want it to go for both of them. So your choices are writing meter per second after each of them, or just stick parentheses around it, cover it that way. Either way,
It shows that it's for both of them.
yes, yeah. So, now we're good. And then, so that answers the first one. The second one, what's the final speed? What do? How do we find final speed? I feel like there are a couple of you who feel like you have it, but aren't feeling the confidence to say it. Take chances, make mistakes. Get messy.
Where's that from?
It's something about distance, isn't it? Yeah.
I would not have said that, depends on how you're gonna link it. Magic School Bus, that's where it's from. So what are you thinking with distance?
Time.
Oh, yeah, no, you're going way complicated.
Can you just add the speed vectors from the objects?
It depends on how you add them. Oh, add the 3 and the 2?
Yes.
No.
Or not,
Yeah.
not add them, but do the same thing that you did with momentum.
Yes. We're gonna add these.
13?
We got, this is 15/13, and this is 16/13.
Okay.
And there's my final, that's my final velocity. But I want the final speed, I'm looking for just the magnitude. So basically I'm doing Pythagorean theorem again, except with 15/13 and 16/13. Instead of 15 and 16 like I did here.
Okay.
Or, in this case, I could have just taken my final momentum here, the magnitude, and divided by the mass of 13.
Mm.
So, I'm gonna write this up and then I'm gonna criticize what I just did. Meters per second. I don't want you ever giving me answers like this. Basically, when you're dealing with a fraction, the numerator and denominator should be whole numbers. Don't give me a decimal on top and a 13 on the bottom. If we were dealing with slide rules and doing this all by hand, yeah, I might be accepting of it, but we have calculators. Go ahead and either turn it into 219 over 130, or use a calculator and actually come up with a decimal. So it's gonna be 1 point something.
685.
And then meters per second is the final speed.
We're dividing or multiplying? Hey, we can multiply, dividing.
Yeah, 21.9 divided by 13. Or, if you've done Pythagorean theorem, you still would have come up with the same answer.
How'd you get the 21.9 again?
Oh, from over here, when we had,
Oh,
the momentum was 15 and 16 in Pythagorean theorem, got you that.
okay, thank you.
Any questions right now?
Right here, we just found the speed of this situation.
After the collision, after they stick together.
Mm-hmm.
Yes.
Okay. And why do we need to do Pythagorean theorem for both of them?
Say it again?
Why do we need to do Pythagorean theorem for both of them?
Because we have, in rectangular form, we have how far it's going in the perpendicular directions. And so when I went magnitude, I'm looking for the hypotenuse of a right triangle. Is that sufficient?
Yeah.
Okay. You seem hesitant.
Eyebrows.
Oh, that's right. One bit of vocabulary that I'm gonna put a nail in the coffin of chapter 6. But it's a vampire, it will rise again. If I have a collision where they stick together, I of course have a vocabulary word to describe that. And I'll get into more detail about this in the next chapter. But they stick together. This is known as a perfectly inelastic collision. Now, the vocabulary of what type of collisions it is can get confusing, so I'm going to talk about the 2 different conventions and then, I guess, 3 conventions because I have my own. But if I talk about there's a perfectly inelastic collision, hopefully you'll immediately think they're going to hit and stick together. And momentum is conserved. Except in the lab where nothing ever works right. All right, we have time to do one more thing. So any questions on momentum? Right, so that's sort of the end of chapter 6. We're not doing a quiz, well, we'll have a test before we do a quiz in chapter 6. But I do 6 and 7 together, and so no need to worry about a quiz on 6 yet. But I want to at least introduce 7. I'm going to start out with a force on A from B. Going back to, we have 2 objects that collide. There's some force being applied to A, and I want to multiply it times the displacement. So that force is applied while it's moving. I'm not going to set up the equality like I did before. I'm just going to start out with this. And there's a dot in between it. It is meant to be a dot. There are other ways of expressing multiplication in math class. Dot is one of them, but this is specifically known as a dot product.
Wait, so it's not multiplication?
It is multiplication. It is specific kind of multiplication. It is a dot product. It is also known as a scalar product. And also, I think much more generally, known as an inner product. That last one is mainly for trivia. I think that might be the last time I talk about it being an inner product, except probably in contrast when I talk about cross products, which are outer products. So dot product or scalar product. It's called a scalar product. Anyone would take a wild guess why it's called a scalar product?
Because that's to do with multiplication?
More than that. That's the product piece. Why the scalar?
Because it's dealing with normal numbers and not vectors.
Oh, no, we've built vectors here.
So she had it.
You went way too general. It's more specific than that. The answer is a scalar. Yeah, we're dealing with vectors. We can't get away from that. But my answer is going to be a scalar. So dot products get rid of the direction. And then it's called a dot product because we use a dot.
Okay. So it's called a scalar product because we're gonna get a number?
Yep, we can get her just a number with units. But.
Oh, yeah.
All right, so let's talk a little bit about dot products here. You're multiplying parallel components. Symbol for parallel, because I didn't feel like writing it out. All right, so let's just take the simplest of the dot products. I have a box here. pushed on with a 5 Newton force. This would be an example of other, because I'm not explaining what's causing it. And it is going to get pushed 3 meters. The dot product is I multiply the parts that are parallel. So my force is 5 newtons, my displacement is going to be 3 meters in the exact same direction. So the force times the displacement is 5 newtons times 3 meters, or 15 Newton meters. For whatever reason, kilogram meters per second, physicists have no problem writing all that out. Newton meters, that's too much. We gotta come up with an abbreviation for that. That is 15 joules.
I think your battery's low.
Ooh,
Screen got darker.
Still recording though. All right, so that's a little bit might get cut off. All right, so a joule, it's called a derived unit. A joule, by definition, is a Newton times meter. Or, which is also a kilogram meter squared per second squared. Which I guess is a Descartes meter per second. This is official, this is accepted by the international community.
So that's joule?
It's a joule. Yeah.
Joule.
Oh, yeah. Named after, anyone take a shot at it?
That one dude,
Yeah.
With a name of?
the last name was Jewel.
I just, and are there any units named after women? Because you said that one dude. There's gotta be.
Think of somebody.
Ada Lovelace has gotta have something named after her. Anyway, all right. So that's the simple one. The force is the same direction of displacement. Done. It's good, slightly more complicated. I have a box that's gonna move to the right 3 meters, and you're pushing it back on it with 5 newtons of force. In other words, you're trying to stop this thing. You got the runaway bus coming at you, and you're doing your Superman routine as you're trying to stop it. You're pushing opposite direction it's moving. The work, I haven't talked about work yet. The force times displacement, it'll end up being negative. So whichever one of them is negative, they're in opposite directions. We'll just make to the right positive out of habit. And so this becomes negative 5 newtons times 3 meters, or negative 15 joules. In the first case right here, we got 15 joules. You're putting 15 joules of energy into the box. Here, you're taking 15 joules of energy out of the box.
Is there a reason why we call it a joule, or that's what it is?
That's what it is. That is the unit.
Use that in nuclear medicine.
Or what was that?
Use that in nuclear medicine.
Joules?
Yeah.
Ah, okay.
You said-
Never quite sure where this stuff actually shows up outside of physics. Like anything outside of physics is of importance. You know what I'm saying? You with me?
With you.
There we go. Anyway, I hope all of you have a safe week. Don't forget, quiz on chapter 4 and 5 next week. It'll be one piece of paper, chapter 4 on one side, chapter 5 on the other. Unless, of course, I forget to say print on 2 sides.
I'll put to, like early November.
Okay. Okay.
We'll get it all figured out.
That's good.
Thank you very much.
Don't forget we have a lab quiz.